In this video, I'm going to share how I tried using machine learning to get better at Jiu-Jitsu. Now, Jiu-Jitsu
उन चीजों से भी आपको familiar कराया जा सके. But for the time being, if
the visual recognition problem.
Around who but all a neural network does is fit a squiggle or a bent shape to data. For example,
Neural networks make predictions, because no matter how we rotate the straight line, it can only accurately predict 2 of the 3 dosages. The good news is that a neural network can fit a squiggle to the data. The green squiggle is close to 0 for low dosages, close to 1 for medium dosages, and close to 0 for high dosages. And even if we have a really complicated data set like this, a neural network can fit a squiggle to it. In this StatQuest, we're going to use this super simple dataset and show how this neural network creates this green squiggle. But first, let's just talk about what a neural network is. A neural network consists of nodes and connections between the nodes. Note, the numbers along each connection represent parameter values that were estimated when this neural network was fit to the data. For now, just know that these parameter estimates
In this video, I'll share 9 of the best GitHub repos for learning AI and machine learning. These are some of the repos I've found helpful along the way, so let's get straight to it. First up, Awesome Lists project. These are community created lists of the most useful resources, tools and materials for a specific technology or topic. There's an awesome list for pretty much every type of technology or topic you could want to learn. But here are the 4 I recommend for AI and machine learning. Awesome Python. Python is the language of AI and machine learning. This repo summarizes the libraries, frameworks and resources covering everything from data visualization to deep learning and NLP. This is one of those repos you'll keep coming back to because it helps you discover the right tools for whatever project you're working on. Awesome Machine Learning. This one zooms in specifically on ML. It's a massive collection of machine learning frameworks and libraries, not just for Python, but for other languages too. Awesome Data Science. It's packed with the best tutorials, books, courses and tools that can guide you from beginner-friendly data projects all the way to advanced topics. And lastly, Awesome MLOps. This one's a bit more advanced, but it's great if you want to take models beyond your laptop and into production. It's full of resources on deploying, monitoring and scaling machine learning systems, which is the real-world side of ML that often gets overlooked. Next up is Roadmap.
Estimates are analogous to the slope and intercept values that we solve for when we fit a straight line to data. Likewise, a neural network starts out with unknown parameter values that are estimated when we fit the neural network to a dataset using a method called backpropagation. And we will talk about how backpropagation estimates these parameters in part 2 in this series. But for now, just assume that we've already fit this neural network to this specific dataset. And that means we have already estimated these parameters. Also, you may have noticed that some of the nodes have curved lines inside of them. These bent or curved lines are the building blocks for fitting a squiggle to data. The goal of this stat quest is to show you how these identical curves can be reshaped by the parameter values and then added together to get a green squiggle that fits the data. Note, there are many common bent or curved lines that we can choose for a neural network. This specific curved line is called Soft Plus, which sounds like a brand of toilet paper. Alternatively, we could use this bent line called ReLU, which is short for Rectified Linear Unit and sounds like a robot. Or we could use a sigmoid shape or any other bent or curved line. Oh no, it's the dreaded terminology alert. The curved or bent lines are called activation functions. When you build a neural network, you have to decide which activation function or functions you want to use. When most people teach neural networks, they use the sigmoid activation function. However, in practice, it is much more common to use the ReLU activation function, or the Soft Plus activation function.
Hello, my name is Andre, and I've been training deep neural networks for a bit more than a decade. And in this lecture,
to life in 3D with this new game changer from Meta. And that is because they just announced SAM 3D, the newest model from Meta that can turn any object or human in 3D based on a single 2D image. And that means we no longer need scanning, multiple angles, expensive setups. No, it can all be done from
function. So we'll use the soft plus activation function in this stat quest. Anyway, we'll talk more about how you choose activation functions later in this series. Note, this specific neural network is about as simple as they get. It only has one input node where we plug in the dosage, only one output node to tell us the predicted effectiveness, and only two nodes between the input and output nodes. However, in practice, neural networks are usually much fancier and have more than one input node, more than one output node, different layers of nodes between the input and output nodes, and a spiderweb of connections between each layer of nodes. Oh no, it's another terminology alert. These layers of nodes between the input and output nodes are called hidden layers. When you build a neural network, one of the first things you do is decide how many hidden layers you want, and how many nodes go into each hidden layer. Although there are rules of thumb for making decisions about the hidden layers, you essentially make a guess and see how well the neural network performs, adding more layers and nodes if needed. Now, even though this neural network looks fancy, it is still made from the same parts, used in this simple neural network, which has only one hidden layer with two nodes. So let's learn how this neural network creates new shapes from the curved or bent lines in the hidden layer, and then adds them together to get a green squiggle that fits the data. Note, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. The first thing we are going to do is plug the lowest dosage, 0, into the neural network. Now, to get from the input node to the top node in the hidden layer, this connection multiplies the dosage by negative 34.4 and then adds 2.14. And the result is an x-axis coordinate for the activation function. For example, the lowest dosage, 0, is multiplied by negative 34.4, and then we add 2.14 to get 2.14 as the x-axis coordinate for the activation function. To get the corresponding y-axis value, we plug 2.14 into the activation function, which, in this case, is the soft plus function. Note, if we had chosen the sigmoid curve for the activation function, then we would plug 2.14 into the equation for the sigmoid curve. And if we had chosen the ReLU bent line for the activation function, then we would plug 2.14 into the ReLU equation. But since we are using soft plus for the activation function, we plug 2.14 into the soft plus equation. And the log of 1 plus e raised to the 2.14 power is 2.25. Note, in statistics, machine learning, and most programming languages, the log function implies the natural log, or the log base e. Anyway, the y-axis coordinate for the activation function is 2.25. So let's extend this y-axis up a little bit, and put a blue dot at 2.25 for when dosage equals 0. Now, if we increase the dosage a little bit and plug 0.1 into the input, the x-axis coordinate for the activation function is negative 1.3. And the corresponding y-axis value is 0.24. So let's put a blue dot at 0.24 for when dosage equals 0.1. And if we continue to increase the dosage values all the way to 1, the maximum dosage, we get this blue curve. Note, before we move on, I want to point out that the full range of dosage values from 0 to 1 correspond corresponds to this relatively narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, and then multiply them by -34.4 and add 2.14, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new blue curve. Bam! Now we scale the y-axis values for the blue curve by -1.3. For example, when dosage equals 0, the current y-axis coordinate for the blue curve is 2.25. So we multiply 2.25 by -1.3 and get -2.93. And -2.93 corresponds to this position on the y-axis. Likewise, we multiply all of the other y-axis coordinates on the blue curve by -1.3, and we end up with a new blue curve. Bam! Now let's focus on the connection from the input node to the bottom node in the hidden layer. However, this time we multiply the dosage by -2.52 instead of -34.4, and we add 1.29 instead of 2.14 to get the x-axis coordinate for the activation function. Remember, these values come from fitting the neural network to the data with backpropagation, and we'll talk about that in part 2 in this series. Now, if we plug the lowest dosage, 0, into the neural network, then the x-axis coordinate for the activation function is 1.2.
வணக்கம் இது Hello.
Alright. I'm going.
What is going on, guys? Welcome back. In this video today we're going to try to understand why we need activation functions in neural networks. What is going on, guys? What is going on, guys? Welcome back. In this video today we're going to try to understand why we need activation functions in neural networks. I'm going to explain the math behind it, and I'm going to show you a code example that illustrates how important activation functions are. So let's get right into it. Alright, so the goal of this video is to understand why we need activation functions in neural networks and why it's oftentimes enough to have a very simple activation function like the ReLU function to make a huge difference when it comes to what a neural network is capable of. So I'm going to give you here first of all the mathematical explanation, and then I'm going to show you a code example that shows that what I'm saying here is actually true and it makes a huge difference. So this video is not going to be very complicated. You don't need to understand a lot about neural networks. You don't need to understand what backpropagation is. You don't need to understand what gradient descent is. The only thing that you need to understand here is how a simple forward pass works in a sequential feed-forward neural network. So how we get from inputs to outputs given the weights and biases. That's the only thing that you need to understand. And for those of you who don't know what I'm talking about, I'm going to give you a 1 or 2 minute crash course here now on neural networks. Very, very superficial, high level, and basic. The basic idea is to have some inputs, whatever they are, x1, x2, x3. You have some neurons, and then these neurons are connected to other neurons in different layers. These are called the hidden layers in here. They can have a different number of neurons, whatever, and in the end we have some output. And the output neurons can be a single neuron, maybe 2 neurons, 3 neurons, doesn't matter. And if these are all now just simple, fully connected dense layers, so to say, we have all the inputs attached to all the neurons of the first layer, we have the output of these neurons attached to all the neurons of the next layer, and so on. And all these connections, this is now important, are weighted connections. So they have weights. Every single connection here that you see has a weight to it. And this weight is a trainable parameter, which means that you don't need to understand how it happens, but there's this backpropagation and optimization process where these weights are adjusted so that the neural network learns how to do a certain task. And every single neuron also has a so-called bias to it. So a constant that is added or subtracted from the weight itself. So maybe to explain this in a more simple way, I'm going to use a very, very basic example here, which is going to be just x is going to be an input, a single input, and then we have 2 neurons here, and then we have 1 output neuron, and that's our neural network. So I feed x into this neuron and into this neuron, and then we have the output of this neuron and this neuron fed into the output neuron, and then we get our output, let's call it y. That is a very simple neural network. And now what we have is we have weight for every connection here. So we would have a weight 1 here, we would have a weight 2 here. Now this is not professional notation. Usually you use some superscript for the layer, but I don't want to confuse now anyone who hears about this for the first time. You have basically different weights here. Let's call them for the sake of simplicity now weight 1, weight 2, weight 3, and weight 4. And what we can do now is, or what happens now is, and of course we also have here the biases. So we have bias 1, bias 2, bias 3. In a simple forward pass, what happens is the input x is now combined with all these weights and biases to produce y. It's a very simple calculation. So yes, it's machine learning, yes, it's neural networks, but at the end of the day, it's just a simple multiplication and addition calculation. So what happens here is x is multiplied by weight 1, x is multiplied also by weight 2. The result of that is fed into these 2 neurons. Then a bias is added. Then we have the result of this whole thing multiplied with weight 4 or with weight 3 if we go the upper route. Then the results here are added together. The bias is then added again, and then we get our input, our output y. So what basically happens is to calculate y, I have to say the following. I'm taking the bias 3. Let me use the colors here. I'm taking the bias 3 plus something. What is this something? This something is weight 3 multiplied with, and I basically just have here weight 1 times x plus some bias.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example.
This is the Python code needed to create and train
Welcome back. So we're talking about neural networks, which is a very powerful, expressive machine learning architecture to learn arbitrary input-output functions, given that you have enough training data. So now I want to walk through a little bit of the architecture and kind of how you build neural networks, what they're made of, things like that. So the basic building block of a neural network is a neuron, which is this little functional unit, kind of an input-output node or neuron. And to be mathematically precise, you have kind of an input signal U that goes into this node, and it does some mathematical operation on U to give you some output Y. And this could be something like just multiplying it by a constant or adding a constant, or it could be more sophisticated. So often people use sigmoidal functions. These are called activation functions, where if U is small, the output is just 0. And if U is large, regardless of how large it is, the output might be 1. And then there's some smooth activation function from 0 to 1. This is a sigmoidal or hyperbolic tangent activation function. Very, very common. Also neural inspired. So a lot of the neurons in your brain kind of have these sigmoidal activation functions. So this is really, really commonly used. Increasingly now people use this kind of this rel-U linear kind of, it's 0 up until a point, and then it grows linearly with U. This is a very useful building block that people are using in modern machine learning architecture. And I can give a whole lecture on all of these different activation functions. There's tons of them. Some are better for something, some are better for others. The rel-U is very common, so is the sigmoidal. So you take that neuron, that unit, and you start to stack it either in series or in parallel or both. So I can put two neurons next to each other and do a more complicated function. This function followed by this function. I can have middle layers. I can, for example, do 3 different functions from this output, and then I can add all those up or multiply them or do some other function downstream. So I can build up this kind of complexity in what's known as an artificial neural network. So here I built up this neural network, the network with nodes and edges describing the topology of how it's connected, but it's artificial. So neural networks, you have neural networks in your head. This is an artificial one built up out of these building blocks. And the different nodes can have different activation functions. They can add up linear combinations of their the previous layer and things like that. Okay? And then if you keep stacking more and more and more of these layers, so each layer is doing some kind of sequential processing. If you start to add a lot of these, then you have something as a deep neural network. And this is the basis of deep learning today. Okay, and so there are a ton of things you can do with these neural network architectures. I'm just going to show you a few here. So this is kind of the neural network zoo. My colleague Nathan Kutz made this image. It was inspired by the Asimov Institute's neural network zoo. This is in our textbook, Data-Driven Science and Engineering. And this just gives you an idea of some of the massive variety of neural network architectures that you can design. And so each color for different nodes means different types of nodes, different types of computations that are happening. There's also the different topology of whether or not information is getting compressed in a bottleneck and expanded, or all these different architectures. And this is only a few of kind of the architectures out there in neural networks. So really there are tons of different, and every year there are dozens of new architectures being proposed to solve different problems. So really as a zoo, there's a ton of different things you can do. And we're increasingly learning through trial and error and study and analysis and lots of hard work by many researchers which architectures are good for which problems. And so again, this is just a few of them. So a couple of key ones I want to point out. Convolutional neural networks, CNNs, are really, really important. These are used a lot in image recognition. The basic idea is if I have a big image that's arrayed here, I don't know if you can see, but it's a smiley face, such as this from Wikipedia. What a convolutional neural network does is it has these convolutional layers that basically take a mask and slide it across the image, doing local computations in local patches. And so what you might be able to do is pull out edges or features, and you run that through a convolutional layer and pull out these edges. And then you might run those through another convolutional layer, another convolutional layer. You stack these convolutional layers, and then you do some processing on them. And so convolutional neural network CNNs are really important for image recognition. Anything where there is a translation invariant. So, if I have a picture of a cat, the cat could be over here, or it could be over here. CNNs can start to pull out kind of this translational invariance that exists in images. Recurrent neural networks are really useful for audio and temporal signals that vary in time, like if you look at the acoustic signature of speech in time. And what these do, I didn't actually draw it, but what you can do is you can add these kind of feedback loops. So you can have the neurons feeding back to themselves, or I can have different layers kind of feeding back. And so this allows you to have this kind of temporal feedback where there's some memory in the system. It's not just a feed-forward network, which is what I showed you before, where all the information just flows from left to right. Here you have this kind of feedback network, this recurrent neural network, because you have memory. So LSTMs, long short-term memory networks, are really useful for audio processing in dynamical systems, anything that varies in time, because they have these kind of feedback signals which allow you to have kind of memory. So there's information that's just living here, kind of getting recirculated through this network. So that's pretty cool. Very, very interesting architecture. Another one that I really like a lot, and I use a lot, is the autoencoder. So here I'm showing you kind of what I think of as a shallow linear autoencoder, meaning that my nodes are doing linear combinations, just taking linear combinations of the input layer. And what the autoencoder is trying to do is take a high-dimensional signal, compress it down to some latent space, this z variable, all the information I need to keep track of, in a way that z information can be kind of lifted back to the high-dimensional image, so that x hat is approximately equal to x. Okay, so this is kind of a compression, decompression, or an encoder-decoder architecture where you can take big data, high-dimensional data, and figure out what is kind of the latent space, what are the degrees of freedom that matter. And so researchers showed a long time ago that you can reconstruct the famous principal component analysis, which has been around for 100 years, in this neural network architecture, this shallow linear autoencoder network. And since then, researchers have massively generalized this to deep autoencoders, where now the node can have nonlinear activation functions that have many layers, and get better compression, better kind of extraction of the essential features of my high-dimensional data in this latent space Z. And that's one of the reasons I like these models, is because there's some interpretability that you get when you do this kind of information bottleneck, this compression down to this latent space, because there might be few enough variables here that I can actually analyze and try to understand what these mean with respect to the data. So I think these are kind of just some neat architectures. You have convolutional neural networks, recurrent neural networks, you have these autoencoder networks, and there's many more. Kind of as much as you can imagine, you can build a network to do it. And maybe that's the last thing I want to point out, is that designing and implementing these architectures is becoming extremely simple because of the explosion of open source software put out by Google and Facebook and others. So you have TensorFlow and PyTorch and Keras, which are these incredibly powerful environments where you can design neural network architectures and then train them with training data to build these very powerful expressive models. So it's really neat and also increasingly easy to design and use.
If you're aspiring to be a scientist or machine learning engineer, then machine learning system design is probably one of the essential skills that you need to know. It's a bridge between just simply building a model and actually bringing it into production to generate tangible business value. The ability to turn ML ideas into production systems that save money, generate revenue, and bring business value ultimately decide your career growth and your salary. I personally build machine learning systems that have saved companies over $1.5 million per year, and these exact skills help me land 100K job offers within data science and machine learning. So in this video, I want to break down exactly how I think about machine learning system design and also help prepare for interviews. Let's get into it. On screen here is the framework I use when I think about building a machine learning system. Let's now break down this framework step by step. The first part is to understand the business problem. Then the first thing to do is basically identify exactly what we're trying to do. So what is break down this framework I use when I think about about building a machine learning system. Let's now break down this framework step by step. The first part is to understand the business problem. And the first thing we need to do is basically identify exactly what we're trying to do. So what is it we're trying to improve? What is it we're trying to measure? Is it user-based? Is it company-based? Like, and when we find it, is the main part of this step of the frame. After we've identified the data, it's now time to do some feature engineering. So the first bit is basically to look or identify the features that we think are important to the problem. Like if we're trying to predict, churn rates, then maybe we want to know more about the pricing or how the users act with the application we're building, right? So just using that business knowledge of what information we think is most relevant to predicting the target variable. We may also want to clean the data, so handling missing values, inconsistent entries, and just data that doesn't look like we want it to be. How do we sort through that and how do we fix it? Machine learning models can only take in numeric data types. So we also want to better represent our features through things like one-on coding, target encoding, and embeddings. And the last thing we will look at is the sampling and splits. So this will be like taking into account unbalanced data sets, understanding if there's any data leakage we may have. Like I said, if more complex models are actually doing a good job. After you've done your benchmark model, you then start training more complex models, and you do things like hard parameter tuning, cross-validation, early stopping, all these best practices around model training, and just into both training and testing when we actually build a model. After we've done all the data and the feature engineering, we're now at the model design and selection part. And this section is all about basically showcasing or showing off your machine learning knowledge theory. In this section, it's really important to start with a benchmark model. You want to start with a really simple heuristic, like loss prediction, mean value. Something that's, like I said, stupid, because you want to benchmark your more complex models against a really simple solution. This is the first step of any form of modeling, in my opinion, because it allows you to basically determine, like I said, if more complex models are actually doing a good job. After you've done your benchmark model, you then start training more complex models, and you do things like hard parameter tuning, cross-validation, early stopping, all these best practices around model training, and you can slowly build complexity on types of models that you're going to try for your target. And one thing you need to take into account whilst building these models is trade-offs. So like interpretability, complexity, inference speed, latency, all these things that impact how your model works in production, you need to keep that back in mind, because that will also impact the type of model that you will eventually ship. After we have our best model or the model we think we're going to use, we then need to think about how we're going to service it and deploy it into production. So the things we need to consider here is infrastructure. Are we going to use cloud systems or on-premise servers? What type of CI/CD pipelines are we going to set up, and how are we going to deal with scalability problems, as well as infrastructure side. You'll also need to think about how we're going to service the model to the customers or to the business. So we can deploy it through an API, it could be an edge model, and are we going to do things like batch predictions or live online predictions all the time? These are all things we need to take into account when building infrastructure and building exactly how we're going to deploy the model into production. And finally, the last part, after the model is deployed into production, we need to think about how we're going to evaluate it and also monitor its progress. The main things we need to think about here is the metrics. So are we going to use a different online metric versus the metric we use for offline testing? How exactly are doing some sort of specialism in a certain area. Nevertheless, if you do want a comprehensive list, but by no means exhaustive, of the things you should learn, then these are following things that you should know from machine learning system design. So for machine learning theory, you should learn supervised learning. So these are things like classification, using models like logistic, regression, support vector machines, and decision trees. You should also know regression, which is linear regression, decision trees, and gradient booster trees. Then, as well as supervised learning, you need to know unsupervised learning. So these are things like clustering, using k-means and DB-scan, dimensionality reduction, and latent semantic analysis. Then after you learn those forms of learning, it then time to learn deep learning. So deep learning will be things like neural networks,
Hello everyone, a very good afternoon. I hope everyone is safe and healthy wherever they are. So this video today is about self-supervised learning, and this is the first part of it, where we'll just the way introduction to the self-supervised representation learning. So let's get started. So first of all, we all know how supervised learning is. So we have unlabeled data, we label it, and then we train the network for the test.
Now we plug 1.29 into the activation function to get the corresponding y-axis value, and get 1.53. And that corresponds to this yellow dot. Now we just plug in dosage values from 0 to 1 to get the corresponding y-axis values, and we get this orange curve. Note, just like before, I want to point out that the full range of dosage values from 0 to 1 corresponds to this narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new orange curve. So we see that fitting a neural network to data gives us different parameter estimates on the connections, and that results in each node in the hidden layer using different portions of the activation functions to create these new and exciting shapes. Now, just like before, we scale the y-axis coordinates on the orange curve. Only this time, we scale by a positive number, 2.28. Boop, 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 boop. And that gives us this new orange curve. Now the neural network tells us to add the y-axis coordinates from the blue curve to the orange curve. And that gives us this green squiggle. Then, finally, we subtract 0.58 from the y-axis values on the green squiggle. And we have a green squiggle that fits the data. Bam! Now, if someone comes along and says that they are using dosage equal to 0.5, we can look at the corresponding y-axis coordinate on the green squiggle and see that the dosage will be effective. Or, we can solve for the y-axis coordinate by plugging dosage equals 0.5 into the neural network, and do the math. And we see that the y-axis coordinate on the green squiggle is 1.03. And since 1.03 is closer to 1 than 0, we will conclude that a dosage equal to 0.5 is effective. Double bam. Now, if you've made it this far, you may be wondering why this is called a neural network, instead of a big fancy squiggle-fitting machine. The reason is that way back in the 1940s and 50s, when neural networks were invented, they thought the nodes were vaguely like neurons, and the connections between the nodes were sort of like synapses. However, I think they should be called big fancy squiggle-fitting machines, because that's what they do. Note, whether or not you call it a squiggle-fitting machine, the parameters that we multiply are called weights, and the parameters that we add are called biases. Note. This neural network starts with two identical activation functions, put the weights and biases on the connections, slice them, flip them, and stretch them into new shapes, which are then added together to get a squiggle that is entirely new. And then the squiggle is shifted to fit the data. Now, if we can create this green squiggle with just two nodes in a single hidden layer, just imagine what types of green squiggles we could fit with more hidden layers and more nodes in each hidden layer. In theory, neural networks can fit a green squiggle to just about any dataset, no matter how complicated. And I think that's pretty cool. Triple bam! Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, the chain rule is cool. StatQuest, yeah. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about the chain rule. And it's going to be clearly explained. Note, this StatQuest assumes that you are already familiar with the basic idea of a derivative and just want a deeper understanding of the chain rule. That said, let's do a super quick review. Imagine we collected these measurements from a bunch of people. On the x-axis, we measured how much they liked StatQuest, and on the y-axis, we measured awesomeness. We can then fit this orange parabola to the data. The equation for the parabola is awesomeness equals likes StatQuest squared. The derivative of this equation tells us the slope of the tangent line at any point along the curve. The slope of the tangent line tells us how quickly awesomeness is changing with respect to likes StatQuest. We can calculate the derivative of awesomeness with respect to likes StatQuest by using the power rule. The power rule tells us to multiply likes StatQuest by the power, which is 2, and raise StatQuest by the power, 2 minus 1. And since 2 minus 1 equals 1, and raising something by 1 is the same as omitting the power, we end up with 2 times likes StatQuest. Okay, bam, that's the review. Now let's dive into the chain rule with a super simple example. Imagine we collected weight and height measurements from 3 people, and then we fit a line to the data. Now, if someone tells us they weigh this much, we can use the green line to predict that they are this tall. Bam. Now imagine we collected height and shoe size measurements, and we fit a line to the data. Now if someone tells us that they are this tall, we can use the orange line to predict that this is their shoe size. Bam! Now, if someone tells us that they weigh this much, then we can predict their height, and we can use the predicted height to predict shoe size. And if we change the value for weight, we see a change in shoe size. Bam! Now let's focus on this green line that represents the relationship between weight and height. We see that for every 1 unit increase in weight, there's a 2 unit increase in height. In other words, the slope of the line is 2 divided by 1, which equals 2. And since the slope is 2, the derivative, the change in height, with respect to a change in weight, is 2. Now, since the slope of the green line is the same as its derivative, 2, the equation for height is height equals the derivative of height with respect to weight times weight, which equals 2 times weight. Note, the equation for height has no intercept because the green line goes through the origin. Now let's focus on the orange line that represents the relationship between height and shoe size. In this case, we see that for every 1 unit increase in height, there is a 1/4 unit increase in shoe size. And I admit that it's hard to see the 1/4 unit increase in shoe size, so just trust me. Anyway, because we go up 1/4 unit for every 1 unit we go over, the slope is 1/4 divided by 1, which equals 1/4. And since the slope is 1/4, the derivative, or the change in shoe size, with respect to a change in height, is 1/4. Now, since the slope of the orange line is the same as its derivative, the equation for shoe size is shoe size equals the derivative of shoe size with respect to height times height, which equals 1/4 times height. And again, because the orange line goes through the origin, the equation for shoe size has no intercept. Shoe size equals the derivative of shoe size with respect to a change in height is 1/4. Now, since the slope of the orange line is the same as its derivative, the equation for shoe size is shoe size equals the derivative of shoe size with respect to height times height, which equals 1/4 times height. And again, because the orange line goes through the origin, the equation for shoe size has no intercept. Now, because weight can predict height, and height can predict shoe size, we can plug the equation for height into the equation for shoe size. Now, if we want to determine exactly how shoe size changes with respect to changes in weight, we can take the derivative of shoe size with respect to weight. And the derivative of the equation for shoe size with respect to weight is just the product of the two derivatives. In other words, because height connects weight to shoe size, the derivative of shoe size with respect to weight is the derivative of shoe size with respect to height times the derivative of height with respect to weight. This relationship is the essence of the chain rule. Plugging in numbers gives us 1/2. And that means for every 1 unit increase in weight, beep, boop, beep, there is a 1/2 unit increase in shoe size. Bam! Now let's look at a slightly more complicated example. Imagine we measured how hungry a bunch of people were and how long it had been since they last had a snack. As time since the last snack increases on the x-axis, people got hungrier and hungrier at a faster rate. So we fit an exponential line with intercept 1/2 to the measurements to reflect the increasing rate of hunger. Then we measured how much people craved ice cream and how hungry they were. The hungrier someone was, the more they craved ice cream. But, after a certain amount of hunger, the craving did not continue to increase very much. So we fit a square root function to the data to reflect how the increase in craving tapers off. Now, if we want to see how the rate of craving ice cream changes with respect to the time since the last snack, plugging the equation for hunger into the equation for craves ice cream gives us an equation without an obvious derivative. To convince yourself that taking the derivative of this is no fun at all, pause the video and give it a try. However, because hunger links time since last snack to craves ice cream, we can use the chain rule to solve for this derivative. First, the power rule tells us that the derivative
example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might.
Welcome. I'm Steve Brunton from the University of Washington, and I'm really excited to introduce you to a new focused short course on kind of an introduction to data science and data-driven engineering, specifically tailored to the aerospace industry. So this is a collaboration between University of Washington faculty and engineers at Boeing to get people rapidly up to speed in the modern, exciting new technologies being developed in data visualization, machine learning, kind of data science in general. So let's get started. This is the overview video, so I'm just going to walk you through the various topics we're going to cover. We're going to start by motivating why is this such an important time now to integrate data-intensive engineering with the aerospace industry. So we're going to start with motivating examples, aerospace case studies, so things like advanced manufacturing, flight test evaluation, design of aircraft wings, things like that. We're going to talk about data visualization. So this is usually our first line of attack when we are working with a data-intensive problem, is to try to visualize the data to understand it. So this is the process of kind of asking and answering questions with data, telling a story with your data, and really understanding what might be possible, again, what problems you might be able to solve. Welcome back. I'm Steve Brunton from the University of Washington, and today I'm really excited to start a new lecture series, which is a part of a larger set of boot camps.
With TensorFlow. In this course, you'll master deep learning concepts and their applications in computer vision tasks, such as image classification, object.
Large I do this step and do this step for the loss of the accuracy. Now this is the position doesn't really matter. All we're interested is in I do this step and do this step. This I do this step and do this step for the loss of the accuracy. All the values before the last we have now all this once. So we have that and that's fine, everything looks fine. Then from here we take this and pass, we'll take this output x1 and pass into our layer norm2, so we call this layer norm2. That's it. 0.5 now. What we get will be negative 0.5 times this have, okay, we should have, let's run this here to have out 2. So we'll have
Hey everyone, welcome to my channel. In this video, we are going to learn how to use gesture control to change the volume of a computer. We will first look into hand tracking, and then we will use the hand landmarks to find the gesture of our hand to change the volume. This project is module based, which means we will be using a previously created hand module, which makes the hand tracking very easy. I have created an
okay. Now that you know what is machine.
What is MLOps? Picture it as DevOps, DataOps, and ModelOps combined. We have a development, staging, and... Did you know that
What is MLOps? Picture it as DevOps, DataOps, and ModelOps combined. We have a development, staging, and production environment.
3 of my favorite resources to learn.
What is
Percent free from
What's your view on ML engineer vs MLOps? What's your view on
MLOps roadmap. So in order to be an MLOps engineer, you need to have primarily 3 skills: data engineering plus DevOps skill set, plus in order to do data engineering or DevOps, you need to have a knowledge on cloud platforms using AWS or Azure or GCP.
Have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment, and 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed an image with, say, a loop up top, like a 9 or 8, there's some specific neuron whose activation is going to be close to 1. I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with the 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with a layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern of several edges to make a loop, and other such things? What we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. And in this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like negative 10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer, and each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add onto the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases, 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposely tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer according to these weights corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra, so for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here, and what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication.
Derivative of hunger with respect to the time since the last snack is 2 times time. Likewise, the power rule tells us that the derivative of Crave's ice cream with respect to hunger is 1 divided by 2 times the square root of hunger. So, with these two derivatives, the chain rule tells us that the derivative of Crave's ice cream with respect to time is the derivative of Crave's ice cream with respect to hunger times the derivative of hunger with respect to time since last snack. So we plug in the derivatives, bip, boop, bip, and plug in the equation for hunger. And cancel out the 2's, and we get the derivative of Crave's ice cream with respect to time since last snack. This derivative tells us how quickly, or slowly, our craving for ice cream changes with respect to time. Double bam! In this last example, it was obvious that hunger was the link between time since last snack and Crave's ice cream, and we had an equation for hunger in terms of time, and an equation for Crave's ice cream in terms of hunger. However, usually these relationships are not so obvious. Instead of having two separate equations, we usually get the first equation jammed into the second. And when all you have is this, it's not so obvious how the chain rule applies. So we can talk about how to apply the chain rule in this situation. Let us scooch the equation to the left so we have room to work. Now, one thing we can do in this situation, the power rule.
Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and a sigmoid switchification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now's the point I suppose I should say subscribe to stay notified about when that video or any new... Alicia, one thing I think we should quickly bring up is this sigmoid function. As I understand it, early networks use this to squish the relevant weighted sum into that interval between 0 and 1, kind of motivated by this biological analogy of neurons either being inactive or active.
Exactly.
But relatively few modern networks actually use sigmoiding.
Yeah.
That's kind of old school, right?
Yeah, or rather, ReLU seems to be much easier to train.
And ReLU stands for rectified linear unit?
Yes, it's this kind of function where you're just You're just taking a max of 0.
ReLU, short for Rectified Linear Unit, is one of the most common activation functions across neural networks. While this video will also brush upon key concepts around neural networks, it expects some prior familiarity with them. The main focus here would be to visualize the effect of ReLU using an example. Let's start by analyzing a single neuron. It receives input from various neurons prior to it, along with a weight W associated with each of these inputs. We also obtain a bias value B, which remains fixed once the model is already trained, and is independent of the input. These cumulatively produce the output activation from the neuron, referred as A. Now obtaining the output A is a two-step process. To understand that, we will zoom into the neuron. First, we do a weighted sum of the inputs from the previous neurons and the bias, referred as Z. The formula for Z is shown below. You may note that Z is a simple real number, and to this we apply the activation function F to produce the final output from the neuron A. So when we talk about activation functions, it just refers to the second operation, the mapping from Z to A. A key requirement from activation function is that it should be non-linear. Its importance will be illustrated later in the video. An activation function also requires its first derivative to be defined at every point. Backpropagation depends upon this property. Let's take a deeper look at ReLU. In its standard form, it mimics the identity function when Z is greater than 0 and is 0 when Z is negative. This fulfills the criterion for non-linearity. Moving on to the next requirement, we may plot the derivative of ReLU is equal to 1 for positive values of Z and 0 for negative values of Z. Interestingly, the derivative is undefined at Z equal to 0. Isn't that a problem? This is handled by fixing the derivative to either 1 or 0 during the training process, and hence we ensure that the first order derivative is defined at every point. The two additional criterions that are sometimes mentioned, boundedness and monotonicity. Both of these are not strictly followed, like ReLU itself is not bounded for positive values of Z, and both swish and mesh activation functions are exceptions to the case of monotonicity. We'll conclude this section by looking at how the value of ReLU varies for different values of Z. When Z is positive, it passes through unchanged, that is, ReLU behaves like a pass-through function, and for negative Z, the output A dies to 0. Also, there are different variants of ReLU. Some of the more popular and distinct ones are listed here. Leaky ReLU. It has a small slope for negative values, instead of the value being all zeros, as in the case of vanilla ReLU. The negative slope is typically equal to 0.01. Next one is called parameterized ReLU. It's a more generic form of leaky ReLU, where the slope for negative Z is a trainable parameter defined by A. ELU. This variation mimics the vanilla ReLU quite closely, while also being truly differentiable everywhere. ReLU 6. This one is bounded both for positive and negative values of Z, and has slope of 1 in range of 0 to 6. These variations, while being very similar to the vanilla ReLU, have their own set of differences. One key thing about these variations is that they share the same fundamental property. They are linear when Z is greater than 0, and either 0 or very small when Z is less than 0. So the following visualization should hold true for any variety of ReLU. Now let's
Hi everyone, I'm Vahid. I'm a data scientist and a machine learning researcher. In this video, I'd like to explain different activation functions so that we can understand how these different functions behave, what their derivatives look like, and finally a few points like their use cases and applications. Here are the 10 activation functions that we are going to study in this video. The table on the left are the 5 most commonly used activation functions, and the table on the right are slightly more advanced activation functions. We are going to go through each one of them and look at their behavior. So let's get started. Our first activation function is a linear function, or simply f of x equals x, which means it will output whatever was passed to it as input. So let's plot this function and see how does it look like. Here is the graph of the f of x equals x, and as you can see, it's just a straight line that passes through origin with a slope of 1. And its derivative is also a constant value of 1, because the slope of this linear function is 1. This simple function is not very useful in artificial neural networks, because it does not do anything to our data. Usually, when we are designing artificial neural networks, we want to have some form of nonlinearities between consecutive layers of the network. So next, we are going to see some nonlinear activation functions instead. Add computer. That output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash outputs.
Hi everyone, I'm Vahid. I'm a data scientist and a machine learning researcher. In this video, I like to explain different activation functions so that we can understand how these different functions behave, what their derivatives look like, and finally a few points like their use cases and applications. Here are the 10 activation functions that we are going to study in this video. The table on the left are the 5 most commonly used activation functions, and the table on the right are slightly more advanced activation functions. We are going to go through each one of them and look at their behavior. So let's get started. Our first activation function is a linear function, or simply f of x equals x, which means it will output whatever was passed to it as input. So let's plot this function and see how does it look like. Here is the graph of the f of x equals x, and as you can see, it's just a straight line that passes through origin with a slope of 1. And its derivative is also a constant value of 1, because the slope of this linear function is 1. This simple function is not very useful in artificial neural networks because it does not do anything to our data. Usually, when we are designing artificial neural networks, we want to have some form of nonlinearities between consecutive layers of the network. So next, we are going to see some nonlinear activation functions instead. The next activation function is ReLU, which stands for Rectified Linear Unit. ReLU is a nonlinear activation function, and it can be represented mathematically in different ways. One way is to use the if condition on the values of x as shown on top, and the other way is simply using the max function as shown in the bottom. Now let's explore the graph of the ReLU function. As you can see here, it outputs 0 whenever the input x is negative, but when x is positive, it will output the same x. The derivative of ReLU is also very simple, and it is shown in the red graph. As you can see, this derivative function has 2 disconnected regions. When x is negative, the derivative or the slope of ReLU is 0. and when x is positive, the slope is 1. And note that it is not differentiable at origin or x equals 0. ReLU and its variants are very popular in building neural networks for adding nonlinearity to network layers. One advantage of the ReLU activation is that it results in sparse models. So neurons that have negative pre-activation values will be turned into 0 by the ReLU activation, and this will make the model sparse. But the drawback of ReLU is that once a neuron activation becomes 0, that particular neuron can no longer affect the parameters of the network effectively, because the gradient of that neuron activation is 0, and 0 multiplied by any value during backpropagation and the chain rule would still be a 0. Our next activation function is the leaky ReLU, which is a modified version of ReLU, or we can say it is a ReLU variant. Here, instead of having a flat 0 for the negative input values, we have a straight line with a small slope as indicated with alpha times x. So alpha is the slope of that line, and this alpha can be between 0 and 1. And here we can see how the graph of the leaky ReLU look like. So it's basically somewhere in between the linear and the ReLU function. If alpha approaches 0, the leaky ReLU function will approach the behavior of the ReLU function. And when alpha gets closer to 1, it will behave similar to the linear function. Now, the derivative of the leaky ReLU is also a discontinuous function. When x is negative, the slope is alpha, and when x is positive, the slope is 1. And note that it is not differentiable at origin. And now we reach our fourth activation function, which is the logistic sigmoid function, or aka sigmoid. The sigmoid function is a smooth version of the step function, and it is mathematically defined as 1 over 1 plus e to the power of negative x. The output of sigmoid can be anywhere between negative 1 and 1, as it is shown in this graph as well. And its derivative is also written as sigmoid of x minus sigmoid squared of x. After we observed that the derivative of ReLU and leaky ReLU were discontinuous functions, now instead we have a function that its derivative is continuous. This derivative function has a peak at the origin, x equals 0, and the two tails, both from left and right, approach 0. It is very important to note that the sigmoid function at its two tails may get saturated. That means when x becomes a very large positive number or a very large negative number, the sigmoid becomes saturated, and as a result, the derivative of sigmoid approaches 0. This is also called the vanishing gradient, which is a common problem in training artificial neural networks. But nevertheless, sigmoid is typically used in the last layer of neural networks for binary classification. Besides that, it is also used as the gating mechanism in recurrent neural networks, such as LSTMs and the GRUs. Our fifth function is the hyperbolic tangent, or tanh for short. Tanh is defined as exp of x minus exp of negative x divided by exp of x plus exp of negative x. And as you can see in the graph of tanh shown in yellow, its output ranges between negative 1 and 1. So next, let's take a look at the derivative of tanh. You can see the formula written in red, but also the shape of the derivative of tanh is very similar to the one for sigmoid. It has a peak in the center or origin and the two tails that zero out. Note that the slope of the derivative of tanh is steeper than the one for sigmoid, and therefore it has less problems with the vanishing gradient. Tanh is sometimes used as a nonlinear activation function in hidden layers of neural networks, but it is less common than the ReLU family. Its special application is in recurrent neural networks, such as the LSTM and the GRU. Now we reach the more advanced activation functions. But before we start with the Soft+, let's recap one of the problems with the ReLU family, either ReLU or the Leaky ReLU. If you recall, the problem with ReLU and Leaky ReLU was that they are not differentiable at origin, or x equals 0. And in fact, they have these discontinuous derivative functions. Soft+ is a smooth version of the ReLU function, and it is differentiable at the origin. It's mathematically defined as the natural log of 1 plus e to the power of x. And as you can see in the graph shown in yellow, it doesn't have that sharp turn at x equals 0, because sharp turns of ReLU will make it non-differentiable. But here we have a smooth curve which makes it differentiable. Now, taking the derivative of the Soft+ function, we get e to the power of x divided by 1 plus e to the power of x. But you can rewrite this function by multiplying both numerator and the denominator by e to the power of negative x. And this will result in 1 divided by 1 plus exp of negative x. And this function is familiar to us. That is our sigmoid function, or the logistic sigmoid. So to summarize, Soft+ is a smooth version of ReLU, and its derivative is the sigmoid function. Next, we have the elastic linear unit, or ELU. This function is defined using a condition on x. When x is positive, the result will be x itself, so no change. And when x is negative, the result of ELU will be alpha times the exp of x minus 1. Now let's see how the graph of ELU look like. As you can see in the graph shown here, ELU approaches negative 1 when x goes to negative infinity. Note that this graph is plotted for alpha equals 1. And for alpha equals 1, if you look carefully at the origin, you will see that the slope of the curve is smooth, before and after 0. So that means the derivative of ELU is a continuous function. This can also be confirmed in the graph of the derivative of ELU. But note that this is only the case when alpha equals 1. If alpha is something other than 1, then ELU is not differentiable at origin, and the derivative will be a discontinuous function. The next activation function is a scaled exponential linear unit, or SELU. SELU was proposed in a 2017 paper titled Self-Normalizing Neural Networks, which basically tries to converge the neurons' activations toward zero mean and unit variance. The mathematical formula of the SELU function is very similar to the one for ELU, except that it has a lambda factor that affects both regions, positive and negative. And the proposed value for lambda is 1.0507, and alpha is supposed to be 1.6732. As you can see, the graph of SELU is also very similar to the graph of ELU. But looking carefully at x equals 0, we can see that there is a sudden change in the slope of the curve before 0 and after 0. This is because alpha is not 1 anymore, and it makes the slope of the curve for the region before 0 and after 0 to be different. As a result, SELU function is non-differentiable at x equals 0, and the derivative of SELU is a discontinuous function. Our ninth activation function is the swish function, which has outperformed both ReLU and the sigmoid in several applications. Swish is mathematically defined as the product of x times sigmoid of beta times x, where beta is a learnable parameter. Note that sometimes you may observe that parameter beta is omitted, which in that case it means it is implicitly set to 1. And if that happens, sometimes it is called the sigmoid linear unit, or SILU. The graph of the swish function with parameter beta equals 1 is shown here. One property of the swish function makes it different from all our previous activation functions, and that is the swish function is a non-monotonic function. So what is a monotonic function? A monotonic function is a function that is always non-decreasing or it is always non-increasing. In other words, a monotonically increasing function is a function that as you increase x, the value of that function will either increase or stay the same, but it will never decrease. And a monotonically decreasing function is the opposite, where as you increase x, the value of that function will either stay the same or decrease. But here for the swish function, we have a non-monotonic function. The reason is, in the beginning, from going from left to right, we can see that at first the value of the swish function will decrease until it reaches a minimum, and then from there it starts increasing. That makes it a non-monotonic function. Now the derivative of the swish function is shown in red, and as you can see, it is a continuous function. However, because the swish function is a non-monotonic function, the derivative of the swish function has both negative and positive values. And for the last function, we have GELU, which stands for Gaussian Error Linear Unit. The mathematical formula of GELU is rather long, as you can see here. So we cannot make any sense of this long equation. So let's instead look at the graph of GELU to understand its behavior. Now we can see clearly that the GELU function is also a non-monotonic function, similar to the swish function. As we trace this function from left to right, by increasing x, GELU starts with a flat region, like almost flat region, and then takes a downward slope until it reaches its minimum. After that, it picks up and starts increasing and passes through the origin. So because it has both decreasing region and an increasing region, it makes it a non-monotonic function. The derivative of GELU also has both negative and positive values, as shown in the red graph. GELU is used in large language models such as BERT or GPT-2. That's it for the 10 commonly used activation functions in neural networks. If you have any comments or questions, please feel free to put your comments down below, and thanks for watching.
rule gives us the derivative of Crave's ice cream with respect to the stuff inside, and the power rule gives us the derivative of the stuff inside with respect to time. Now we just plug the derivatives into the chain rule, and plug in the equation for the stuff inside, cancel out the 2's, and we get the derivative of Crave's ice cream with respect to the time since last snack. And that's exactly what we got before. Bam! Now let's look at how the chain rule applies to the residual sum of squares, a commonly used loss function in machine learning. Note, if this does not make any sense to you, just imagine I said, now let's look at one last example. Imagine we measured someone's weight and height, and we wanted to fit this green line to the measurement. Now, to keep things simple, let's assume we can only move the green line up and down. The equation for the green line is height equals the intercept plus 1 times weight. And we can change the intercept. But, to keep things simple, we can't change the slope, which is set to 1. If we set the intercept to 0, then this location on the green line is the predicted height. And we can calculate the residual, the difference between the observed height and the value predicted by the line. And we can plot the residual on this graph, which has the intercept on the x-axis and the residual on the y-axis. If we change the intercept here, then we can see the change in the residual here. And because a common way to evaluate how good the green line fits the data is the squared residual, we can plot the squared residual here, where we have the residuals on the x-axis and the squared residuals on the y-axis. Now, if we change the intercept here, then we change the residual here and here. And changing the residual here changes the squared residual here. In order to find the value for the intercept that minimizes the squared residual, we are going to find the derivative of the squared residual with respect to the intercept. And then we're going to find where the derivative equals 0, because, given the function y equals the residual squared, the derivative is 0 at the lowest point. The chain rule says that because the residual links the intercept to the squared residual, then the derivative of the squared residual with respect to the intercept is the derivative of the squared residual with respect to the residual times the derivative of the residual with respect to the intercept. The power rule tells us that the derivative of the residual squared is just 2 times the residual. So let's plug that in. To solve for the derivative of the residual with respect to the intercept, we move the equation for the residual over here so we have room to work. Then we plug in the equation for the predicted height. Then, in order to remove these and plug in the they weigh 1.5, we can use the line to predict that they will be 1.9 tall. So let's learn how gradient descent can fit a line to data by finding the optimal values for the intercept. Gradient descent is descent at estimating parameters
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer, plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust, and it's these values that determine what exactly the network, actually does. And what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a tree, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that. It takes as its input those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are. And the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of the situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative. If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill. And notice, even for this really simplified single input function, there are many possible valleys that you might land in, depending on which random input you start at. And there's no guarantee that the local minimum you land in is going to be the smallest possible value of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller. And that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with two inputs and one output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples.
Hello everyone, Dr. Hello everyone, Dr. Data Science here to teach you data science. And if you want to find, hello everyone.
Hello and welcome to Multivariable Calculus. So I think I should probably start off by addressing the elephant in the living room here. I am sadly not Sal, but I'm still going to teach you some math. My name is Grant. I'm pretty much a math enthusiast. I enjoy making animations of things when applicable, and boy is that applicable when it comes to multivariable calculus. So the first thing we got to get straight is, what is this word multivariable that separates calculus as we know it from the new topic that you're about to study? Well, I could say it's all about multivariable.
what would you say are the prerequisites for somebody to take the deep learning specialization in terms of maybe math or programming background?
Need to understand basic programming since there are programming exercises in Python. And the math prereq is quite basic, so no calculus is needed. If you know calculus, is great. You get better intuitions.
The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with two inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with two inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with two variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second variable. That at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. Alright, let's zoom out and sum up where we are so far. The network itself is this function with 784 inputs and 10 outputs, defined in terms of all of these weighted sums. The cost function is a layer of complexity on top of that. It takes the 13,000 weights and biases as inputs and spits out a single measure of lousiness based on the training examples. And the gradient of the cost function is one more layer of complexity still. It tells us what nudges to all of these weights and biases cause the fastest change to the value of the cost function, which you might interpret as saying which changes to which weights matter the most. So, when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Well, the one that I've described here, with the 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, well, it's not bad. It classifies about 96% of the new images that it sees correctly. And honestly, if you look at some of the examples that it messes up on, you kind of feel compelled to cut it a little slack. Now, if you play around with the hidden layer structure and make a couple tweaks, you can get this up to 98%. And that's pretty good. It's not the best. You can certainly get better performance by getting more sophisticated than this plain vanilla network, but given how daunting the initial task is, I just think there's something incredible about any network doing this well on images that it's never seen before, given that we never specifically told it what patterns to look for. Originally, the way that I motivated this structure was by describing a hope that we might have. That the second layer might pick up on little edges, that the third layer would piece together those edges to recognize loops and longer lines, and that those might be pieced together to recognize digits. So, is this what our network is actually doing? Well, For this one at least, not at all. Remember how last video we looked at how the weights of the connections from all of the neurons in the first layer to a given neuron in the second layer can be visualized as a given pixel pattern that second layer neuron is picking up on? Well, when we actually do that for the weights associated with these transitions from the first layer to the next, instead of picking up on isolated little edges here and there, they look, well, almost random, just with some very loose patterns in the middle there. It would seem that in the unfathomably large 13,000 dimensional space of possible weights and biases, our network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on the patterns that we might have hoped for. And to really drive this point home, watch what happens when you input a random image. If the system was smart, you might expect it to either feel uncertain, maybe not really activating any of those 10 output neurons or activating them all evenly, but instead, it confidently gives you some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. Phrased differently, even if this network can recognize digits pretty well, it has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined unmoving digits centered in a tiny grid, and its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So with this as the image of what those second layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how you learn, that'll only happen if you engage actively with the material here somehow. One pretty simple thing that I want you to do is just pause right now and think deeply for a moment about what changes you might make to this system and how it perceives images if you wanted it to better pick up on things like edges and patterns. But better than that, to actually engage with the material, I highly recommend the book by Michael Nielsen on deep learning and neural networks. In it, you can find the code and the data to download and play with for this exact example, and the book will walk you through step by step what that code is doing. What's awesome is that this book is free and publicly available, so if you do get something out of it, consider joining me in making a donation towards Nielsen's efforts. I've also linked a couple other resources that I like a lot in the description, including the phenomenal and beautiful blog posts by Chris Olah and the articles in Distill. To close things off here for the last few minutes, I want to jump back into a snippet of the interview that I had with Lisha Lee. You might remember her from the last video. She did her PhD work in deep learning. And in this little snippet, she talks about 2 recent papers that really dig into how some of the more modern image recognition networks are actually learning. Just to set up where we were in the conversation, the first paper took one of these particularly deep neural networks that's really good at image recognition, and instead of training it on a properly labeled dataset, it shuffled all of the labels around before training. Obviously, the testing accuracy here was going to be no better than random, since everything's just randomly labeled. But it was still able to achieve the same training accuracy as you would on a properly labeled dataset. Basically, the millions of weights for this particular network were enough for it to just memorize the random data, which kind of raises the question for whether minimizing this cost function actually corresponds to any sort of structure in the image, or is it just, memorization?
Memorize the entire data set of what the correct classification is. And so a couple of, half a year later at ICML this year, there was not exactly a rebuttal paper, but paper that addressed some aspects of like, hey, actually these networks are doing something a little bit smarter than that. If you look at that accuracy curve, if you were just training on a random data set, that curve sort of went down very slowly in almost kind of a linear fashion. So you're really struggling to find that local minima of possible.
Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this.
Language and meaning of the relevant maths, covariance, which shows you how 2 variables relate, random variables, common probability distributions like the normal, binomial, and uniform, the normal behavior, and without In this video, I'm going to break down the essential math you need for AI and machine learning. I'll also share the exact roadmap and resources that have helped me along the way. Let's get straight to it. Hi, I'm Harry. I'm an AI master's student here in the UK, and I spent the last year learning a lot of the essential math behind artificial intelligence. Along the way, I picked up key concepts and some practical resources that made a huge difference for me. First up, why should you even learn math? With packages like scikit-learn, PyTorch, and TensorFlow that abstract a lot of the math for you, you can be totally competent without knowing all the underlying details. For example, you can build and deploy a model without ever manually working through gradient descent or fully understanding how it works. However, problems can arise, whether it's debugging training issues or interpreting model behavior, and without some sense of the language and meaning of the relevant maths, you can struggle to work out what's gone wrong or how to fix it. That said, it's perfectly fine to begin without complete deep understanding of the math. As you continue learning and working on projects, gradually building up your math skills will make things clearer. Alright, with that out of the way, let's now talk about the actual math topics and concepts you want to learn. There are three main areas you want to focus on. These form the foundation for most of the algorithms, models, and techniques you'll come across in AI machine learning. Starting with statistics and probability. Having a solid statistical intuition helps you choose the right algorithm for the problem you're trying to solve, and just as importantly, for the data you're working with. A lot of the time, you don't need anything overly complex. If you understand what your data is telling you, simple models can go a long way. This can save you time and reduce complexity. Plus, when you actually understand the math behind your algorithms, tuning them becomes way easier. You have a much clearer sense of what each hyperparameter is doing and how it affects your model, rather than just guessing and hoping something sticks. The key concepts to focus on here include things like populations and sampling that lets you work with subsets of data, the mean, median, mode, and expected values, variance, which tells you how spread out your data is, and covariance, which shows you how two variables relate. Random variables, common probability distributions like the normal, binomial, and uniform. The normal distribution in particular shows up all over the place in data science and machine learning, so it's worth getting really familiar with. The central limit theorem, conditional probability, so understanding how the likelihood of one event changes based on another. Bayes' theorem, maximum likelihood estimation, which is all about estimating the parameters of a model by finding the values that make the observed data most likely. And last but definitely not least, linear and logistic regression. Next is linear algebra. This is the language of data in machine learning. Whether you're working with images, text, or tabular data, it can all be represented as vectors and matrices. Understanding how to work with these structures is key, especially as you get into deep learning. Here you want to get comfortable with scalars, vectors, which you can think of as a list of numbers, matrices, which extend vectors into 2D grids of numbers, and tensors, which are generalizations of all of these to any number of dimensions. Matrix operations like addition, subtraction, multiplication, and transposition, as well as determinants and inverses, which are important for solving systems of linear equations and optimization problems. Matrix rank and linear independence, eigenvalues and eigenvectors, matrix decompositions such as singular value decompositions, and lastly, principal component analysis, which can help to reduce the dimensionality and number of features in your datasets. Finally, there's calculus, particularly multivariable calculus and differential calculus. This comes into play when you're training models. For example, in understanding how gradient descent works to minimize loss functions. You don't need to be able to solve complex integrals or memorize every rule, but having a solid grasp of a few core ideas will make a big difference. Firstly, derivatives and gradients. Derivatives tell us how a function changes, and gradients extend this idea into multiple dimensions. These are essential for then understanding how algorithms like gradient descent adjust model parameters to reduce error and improve performance. Vector or matrix calculus, i.e. the calculus of multiple variables. This includes concepts like the Jacobian and Hessian, the chain rule. This is really at the heart of how backpropagation works in neural networks. And lastly, the fundamentals of optimization. Things like local versus global minima, saddle points, and convexity will help you understand why certain models converge well, while others might get stuck or overfit. Alright, so now that we've covered what maths is important, I want to wrap up by showing how I actually went about learning it, and some of the resources that helped me the most. I'll leave links to these in the description. First, I found it really helpful to begin with a visual and intuitive grasp of the core concept before reading any textbooks or working through practice problems. For this, I highly recommend the YouTube channel FreeBlue1Brown, especially his video series on the essence of linear algebra and calculus. These videos will give you a really solid introduction and appreciation for how these ideas actually work. After that, I moved on to the Mathematics for Machine Learning specialization by Imperial College London on Coursera. It covers both linear algebra and multivariable calculus, and it's taught in a really practical, clear way. That said, it doesn't go into statistics or probability, so to fill that gap in, I turned to Khan Academy's series on this. To go a bit deeper, especially into how these ideas apply specifically to machine learning, I also read through parts of an introduction to statistical learning. It's a great book with real-world examples, and it helps connect the theory to actual ML techniques. Lastly, a final recommendation I've just finished recently is the Mathematics for Machine Learning ebook. It does a good job of tying everything together and showing how the concepts mentioned in this video are actually used to build machine learning algorithms. If you found this video useful, you might like to check In this video, I'm going to break
If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it